Welcome to Math 125. We are going to start this semester by reviewing some important concepts from college algebra that we'll be using this semester. I want to start by quickly reviewing the idea of function notation. Function notation is that f of x that we use for outputs instead of the letter y. And I think the thing to remember that whatever's inside the parentheses is your input or your x value. So if I want to find f of negative 2, I just take the negative 2 and I plug that in for all of the x's. So that would give me 4 plus 4, or 8. This problem is telling me that when x is negative 2, the y value is 8. Now we can plug in things that aren't numbers, we can plug in variable expressions, and it works the exact same way. If I want to find f of 3t, I am going to plug the 3t in for x. I replace both of the x's with 3t. 3t squared would be 9t squared. 2 times 3t is 6t. And that expression is my solution. All right, one more. F of x plus h. Again, whatever is inside that parentheses, this time the x plus h, gets plugged in for the x's. So that would be x plus h squared minus 2x plus h. And I can expand this and see if I have any like terms. Let's see, x plus h squared, that would be x squared plus xh plus xh plus h squared. And then I can distribute the minus 2. And it looks like the only like terms we have is the 2xh. And so this kind of long expression would be my final answer. All right, so the important thing is that the thing inside the parentheses is always what you plug in for the x. The next thing I'd like to review is the concept of domain. Domain refers to basically just the set of all inputs. What kind of x's are you allowed to plug into a function? And so to find domain, we have to remember what kind of restrictions we have with various operations and various types of functions. And so over to the right, I have a list of some of the kind of important restrictions that come up when you're finding domain. So if you have a rational function, which is basically an algebraic fraction, to find the domain, you use the idea that you can't divide by 0. Division by 0 is undefined. So you say the denominator can't equal 0. If you have a square root, we're going to use the fact that the thing inside the square root, the radicand, has to be bigger than or equal to 0. The idea is you can't take the square root of something that's a negative number. This is true for all even roots as well, fourth roots, sixth roots, etc. And then finally, if we have logarithms, the thing inside the logarithm has to be a positive number. It cannot be a negative, and it can't be 0. All of the other functions that we deal with don't really have any restrictions. And so let's just do some examples. Example A, if I want to find the domain of f of x equals 2x minus 5, the first thing I notice is that this is a linear function. If I were to graph it, it would look like a line. And if I think about the graph, that helps me realize that the domain has to be all real numbers from negative infinity to positive infinity. That's because the line continues in both directions forever. In addition, if I look at my list, this linear function doesn't have a fraction in it, doesn't have a square root, doesn't have a log. And so we could even just add to our list, I guess, everything else that we see. So if it doesn't have a fraction, a log, or a square root, it's going to have a domain that's all real numbers. Okay, example B, this time I see a square root. Anytime I have a square root, I take the thing inside the square root, and that has to be bigger than or equal to 0. I can solve this for x by subtracting the 1, and then we could divide by 3, and so I get x is bigger than or equal to negative 1/3. In interval notation, that would be negative 1/3 to infinity. Notice I used the brackets with the negative 1/3 to include that value. That value is part of the domain. All right, example C, h of t is 4 over t squared minus 9. This is a rational function. This is a fraction. And so the rule is, anytime we have a fraction, the denominator, which in this case is t squared minus 9, cannot equal 0. We're not allowed to divide by 0. So I'm going to solve this by factoring. T squared minus 9 is a difference of perfect squares. I can factor that as t plus 3, t minus 3. And that tells me that t cannot equal negative 3 or positive 3. In interval notation, this is going to be everything that's smaller than negative 3, everything between negative 3 and positive 3, and everything bigger than positive 3. All right, I've got 2 more domain examples. Example D, y of p is natural log of p. Anytime we see a logarithm, regardless of what the base is, the rule is that the thing inside the log, in this case it's just p, has to be bigger than 0. And so that's it, in interval notation. My domain would be everything from 0 to infinity. This time I'm using parentheses instead of brackets because 0 is not actually included in that domain. And then finally, part E. Let's see, this is actually a polynomial. More specifically, it's a quadratic function. I don't see a fraction. I don't see a square root. I don't see a logarithm. And so that means my domain has to be all real numbers. I could also think of this graphically. Because this is a quadratic function, I know that its graph is going to be a parabola, and I can visually see that the arrow goes to the right forever, the arrow goes to the left forever, so the domain has to be all real numbers. The third thing I want to review is working with logarithms and exponentials. Those are things that are going to pop up throughout this course. They're functions that we need to be familiar with. And so on the screen in red, I have the definition of a logarithm written down. Basically, every single logarithm can be written in exponential form, and every single exponential can be written in log form. And so the first thing I want to do in this kind of quick review is practice rewriting expressions in the other form. So if I have log base 3 of x equals r, in exponential form, let's see, the base is 3. It would be 3 to the r, logarithms always equal exponents, equals x. That is an equivalent exponential form. In part B, we have a natural log of 2x minus 4 equals 5m. Natural logs mean you have base e. So that natural number e, which is 2.7 something, is actually the base. So the base is e. Logarithms always equal exponents, so e to the 5m equals 2x minus 4. So really what I'm doing here is just using that formula I have circled in red. That's the definition of our logarithm. Now we should be able to go in the opposite order as well. 7 to the x minus 1 equals g, I can write that as a log. So I would start by writing the log. The base of the logarithm is that 7. It's the base of the exponential. So it's going to be log base 7 of g equals the exponent, x minus 1. Again, I've just used that formula that's in red. Okay, same thing for part B. I have 10 to the y equals b plus 1. So that's going to be log base 10. Let's see, of b plus 1 equals the exponent. Logarithms always equal exponents. Now, base 10 is actually a really common logarithm. And so we typically don't actually write the 10. And so I would actually write this as just log b plus 1 equals y. So if you see a log without a little number, without a base, you always assume that it's base 10. If you see an ln, you always assume that it's base e. All right, let's evaluate some logarithms. And this is where we're going to have to use this idea that logarithms always equal exponents. We're trying to find the exponent. So ln1 equals something. We don't know what that is. That problem in exponential form would be e, the base is e, to what power equals 1? And the answer is 0. E to the 0 is 1. In fact, anything to the 0 is 1. So ln1 equals 0. ln e, that's asking me e to what power equals e, and the answer there would be 1. All right, log base 2 of 8 means 2 to what power equals 8, and 2 to the third is 8. Again, notice those answers are always your exponents. Log base 3 of 9 is asking us 3 to what power equals 9. The answer is 2. And finally, log base 5 of 1/5 means 5 to what power is 1/5. That's going to be a negative 1. Negative exponents, remember, mean reciprocals or fractions. So 5 to the negative 1 is actually 1 over 5. So I have quite a bit of review material I want to get through, and so I'm going to stop this video here and finish it up in part 2.